Hello students, my name is Shashank Shekhar. So let us continue with the chapter some basic concepts of chemistry. So if you talk about a chemical reaction, then reaction is say represented with the help of this equation that is called chemical equation, in which the left hand side of the arrow, on the left hand side of the arrow we have reactants, and on the right hand side of the arrow we have the product. Now each of the reactants, for some reactants you will see that it is led by a number. Okay, so you can see here for these two reactants they have a number before their symbols. So this numbers can be there or cannot be there, and these numbers are called stoichiometric coefficient. If it is not there, that means that the stoichiometric coefficient of CO2 is 1 and the stoichiometric coefficient of CH4 is 1. Now the stoichiometric coefficient is very important, and it is very important. Why it is important? Because it gives you the amount of substance that is reactant, or the equivalent of substance that is reacting, right? Now for a given reaction, it is such that the reaction is balanced. Okay, so if you have learned the balancing of reaction in class 10, then you must have seen that we place this coefficient to balance a given chemical reaction, right? Now if what can be derived from this chemical equation? uh, there are 2 to 3 points that can be derived from this single chemical equation. We can say that one molecule of methane reacts with two molecules of oxygen to give one molecule of carbon dioxide and two molecule of water. So that's a statement. Or we can also say 1 mole of methane react with 2 moles of oxygen to give 1 mole of carbon dioxide and 2 mole of water. So both of statements are true, right? So there is no difference in this. Means the statements are different, but we can say both of this from the given chemical equation. Clear? Now let us move further. So here we have seen that methane and dioxygen are the reactants and carbon dioxide and water are the products. Note that all the gaseous with all the reactant and products are gases in the above reaction, and this may be indicated with the help of letter G. So you can see another specification here. What is the another specification? That these formulas are led by, means are say suffixated with a symbol say G in this case, this case and this case. So all of these are having G. So what is the meaning of this G? This G means they are in the gaseous state, whereas the coefficient for O2 is 2 and for H2O is 1. Similarly, the for H2O and O2 the coefficient is 1, and for methane and carbon dioxide the coefficient is 1. Oxygen is having coefficient of 2, H2 is having a coefficient of 2, CH4 and CO2 are having coefficient of 1. Now they represent the number of moles, molecules and moles both. So as I have told you, they can represent both, either molecule or mole, taking part in the form of reaction. So we can also say, what we can say from this reaction, methane and oxygen are reactants. So methane and dioxygen are reactants, and carbon dioxide and water is the product. 2 moles of O2 and H2 are taken. Now, what is the meaning of this is the number of moles? So we can say that 1 mole of CH4 react with 2 moles of dioxygen to give 1 mole of carbon dioxide and 2 mole of H2O. What does it mean? So 1 mole of methane contains how many number of methane? So as I have told you, this value will never change. So therefore 6.022 into 10 to the power 23 CH4 molecules react with 2 into 0.6022. Why? Because 2 moles are taken, so 2 multiplied by 6.022 into 10 to the power 23 O2 molecules. So they both react to give, again, one means 6.022 into 10 to the power 23 CO2 and 2 into 6.022 into 10 to the power 23 H2O. Okay, so this much molecules of methane react with this much 2 into Na molecules of O2 to give Na molecules of CO2 and 2 into Na molecules of H2O. So we can see this also, or else we can say one molecule react with 2 molecules of water, oxygen, to give 1 molecule of carbon dioxide and 2 molecule of H2O. See, this much information can be processed from this single equation, right? From a balanced equation, I would say. Clear? Now next. So same thing is written here. 1 mole of this react with 2 moles of oxygen to give 1 mole of CO2, 2 moles of H2O. 1 molecule of CH4 react with 2 molecules of O2 to give 1 molecule of CO2 and 2 molecules of H2O. We can say this in terms of volume also. How? Now 1 mole of CH4 will contain this much liter. So it is fixed. So this is fixed, right? So the thing is fixed that 1 mole of any gas at standard condition, that is STP, will always contain 22.4 liters of that gas. Means 1 mole of gas at STP, that is 1 atm pressure and 27 degrees Celsius, will be contained in 22.4 liter volume. Okay, clear? 22.7. Now since we are doing this reaction at STP, therefore 1 mole of methane will contain 22.7 liter of methane gas, and 2 moles of oxygen will contain 22.7 into 2, that is 2 7 14, 2 to the 4 and 5, 2 to the 4, that is 45.4 liter of oxygen, and they will react to give 22.7 liter of carbon dioxide. This will be not here, and 45.4, again 45.4, because 2 moles of H2 are present, so 45.4 moles of H2. Now we can represent this same thing in terms of mass. How? So for that you must know the molar mass. So CH4, O2, CO2, H2O. Now what is the mass of 1 mole of methane? Anyone? So for that we have to calculate the molecular mass. So atomic mass of carbon is 12, and atomic mass of hydrogen is 4. So 4 into 1. So that would give us 12 plus 4, 16 gram. Now if I talk about oxygen, so 16 into 2, so 2 oxygens are present, and it is again multiplied by 2 for 2 moles. So that is 64 grams of oxygen. Talk about carbon dioxide. So we have mass of carbon as 12 and oxygen as 62. Since 2 oxygens are present, therefore 16 into 2. That would give us 32 plus 12 or 44. Now its molecular mass is 18. 18 into 2, 36 gram. So 16 gram of methane, 64 gram of oxygen, 44 gram of CO2, and 36 gram of H2O. So we have got 4 pieces of information. First in terms of molecules, also in terms of moles, and also in terms of volume and mass. So if you have to calculate the density, you can calculate the density also. How? So we know that density is equals to mass per unit volume. So we got the mass, and what was the volume of this mass? It was 22.4. So if I talk about the density, we can talk about the density also. Very clear? Okay. Now, next, what is limiting reagent? What is limiting reagent? So whenever we do a reaction, we take some amount of reactant A. Say we have reactant A and reactant B. So we take some amount of reactant A and some amount of reactant B. Now suppose the reaction proceeds and all of the A has been consumed, but the B is still left in the reaction mixture. So in that case, we will call A as the limiting reagent. Why the limiting reagent? Because it is limiting our reaction. So we call it as limiting reagent. Okay. So many a times reactions are carried out with amounts of reactant that are different than the amounts that is required by the balanced chemical reaction. Now how can we explain it? So if you talk about the previous example, so we have seen that 16 gram of methane is taken. Now instead of 16 grams, suppose we take 12 gram of methane. So in that case, what will happen? All of this 12 gram will be consumed, but we will be left with some amount of oxygen, because 64 gram react with 16 gram, but 64 gram will not totally react with 12 gram. That would leave us some amount of oxygen, and in that case, we will call the oxygen as the methane as the limiting reagent. Clear? So the reactant which is present in least amount gets consumed after some time, and after that further reaction does not take place. So whatever with the amount of other reactant is taken. So hence the reactant which get consumed first limits the amount of product and is called a limiting reagent. So this is also a very good statement. So the reactant which get consumed first and limits the amount of product that is being formed is called the limiting reagent. Okay. Now to make our things life easier, what we did, so rather than considering moles and all, we take some say mnemonic devices. So those mnemonic devices we can tell them as mnemonic devices because we have taken a shortcut, right? So to say deal with this number of molecules or number of moles or mass is very difficult. So for instead of that, we have introduced some terms. So here the terms are mass percentage, mole fraction, molarity. Now we will talk about each of them in detail. Let us start with the mass percent. So what we have done, instead of seeing the theory, let us do a question. So the question says that a solution is prepared by adding 2 gram of substance to 18 gram of water. Calculate the mass percent. What is the mass percent? So if you are adding 2 gram and 18 gram, so according to laws of conservation of mass, the total mass would be 18 plus 2, that is 20 gram. So see how important is the laws of conservation of mass here. So it is a direct application. So therefore, the total mass of solution would be this much. Now we have to calculate the mass percent of this A. So that is 2 gram. So 2 by total mass, that is 20 into 100, that is 10%. So there's nothing rocket science in this. We have used the simple formula of percentage. So the percentage formula is, suppose you are scoring 64 out of 100. So your percentage will be 64 by 100 into 100. Means the marks obtained by total mass into 100. So here also we have to calculate the mass percent of this A. So the mass of A divided by the total volume of total mass of solution. Total mass of solution is mass of solute plus mass of solvent. So solute is 2 gram and solvent is 18 gram. So 2 by 2 plus 18 into 100. That would bring us to 10% as the answer. Next is mole fraction. What is mole fraction? So let me make one point clear here. So this mole fraction is mostly used for gases. Okay, it is mostly used for gases rather than liquids and gas. So we'll see it later. So the later on terms, that is molarity and molality, that are defined in terms of volume and mass. And since we know that gases do not have a fixed volume or definite shape, so therefore to take the mole fraction of those would be more appropriate because number of moles would be fixed. It will not change for a closed system. Now it is the ratio of number of molecule for a particular component to the total number of solution. So here what we are taking the relative number of moles. Okay. So suppose Na is the number of moles for A species and Nb is the number of moles for B species. So the mole fraction would be, so for mole fraction of A, it would be number of moles of A divided by number of moles in the solution. Got it? So we can tell it in this way, that it is the relative abundance, or relative amount of A that is present in terms of moles. So moles of A divided by total number of moles. So suppose it is a binary solution that contains only A and B, that is two reactants. So therefore number of moles of A divided by total number of moles, that is Na plus Nb. Similarly for B, total number of moles of B by Na plus Nb. So the mole fraction of A and mole fraction of B. Now since this both are of a same part, so it can be explained in this way. So suppose we have a cake. Out of this, 3/4 is consumed by, say, blue color, and rest of this is consumed by, suppose, green color. Now if you take the fraction of both of this part and add both of this, then you will get 1. So similarly, mole fraction of A per mole fraction of B will be equals to 1. This mole fraction is represented by chi, and with a subscript, that is for the given species for which you are calculating, that is chi A and chi B. So therefore chi A plus chi B, since only 2 species are present, so chi A plus chi B is equals to 1. Now if you are given the mole fraction of A and you are asked to calculate the mole fraction of B, how you will calculate? So chi B will be nothing but 1 minus chi A. See, very simple to calculate, but this is only for a binary solution. So if we have chi A plus, suppose, chi A, B and C, 3 species, and now you are asked to calculate the mole fraction of, say, A and it's given of B, then you cannot calculate. But if you have to calculate the for C, A or B, and out of these 3 the 2 are given, then you can calculate it. Okay, so you can calculate for 1 only, given that the rest of the mole fraction of the rest of the 1 is given. So suppose we have chi A, chi B and chi C. So therefore chi A plus chi B plus chi C is equals to 1. Now suppose chi B and chi C are given, and you have to calculate for chi A. So that would be 1 minus chi B plus chi C. Clear? This is called as mole fraction. Next is molarity. So this is the most important one, and this will be used to and fro whenever you are given a reaction mixture in a solution, that is a liquid state. So what is the definition of this? So definition of this is that molarity is the number of moles of solute divided by total volume of the solution in liter in which the solute is dissolved. Now each of these things are important. First we have to take the number of moles of solute. We have to put it in the numerator. Then in the denominator, we will take that volume of solution in which that solute is dissolved. And that volume should be always in liters. For those who do not know the conversion, so this conversion is very important. 1 liter is equals to 1 decimeter cube. Therefore, we can also say that it is defined as the number of moles that is dissolved in 1 decimeter cube of the solution. So how you will calculate it? Suppose we have an example here, illustration here. So it is said that we want to prepare 0.2 m. So this m is the representation for molarity. So it is written against the molarity value. And 1 m NaOH means 1 mole of NaOH present in 1 liter of solution. So for 0.2, how many moles of NaOH is dissolved in 1 liter? 0.2 moles. So suppose it is written that xm is the molarity of the solution. That means x moles, suppose xm is the molarity of the A. That means that x moles of A are dissolved in 1 liter of solution. Is it clear? So if we say that 1 molar NaOH, so it is also termed as 1 molar. So 1 molar NaOH means 1 mole of NaOH is present in 1 liter of water. Similarly, or a solution. Similarly, if we say that 0.2 molar solution of NaOH, that means 0.2 moles of NaOH is present in 1 liter of solution. Next, hence for making 0.2 m solution from 1 mole, we have to take that volume of 1 NaOH which contains 0.2 mole of NaOH and dilute the solution with water to 1 liter. Now how much volume of concentrated 1 m NaOH should be taken which contains 0.2 mole of NaOH? So what are we doing here is that we are taking 1 molar NaOH and we are trying it to convert it into 0.2 molar NaOH. So for that, what are we doing? First of all, we are taking that volume of NaOH which contains 0.2 moles of NaOH. Okay, so we are given that we have 1 molar solution, and we are given that we have to get 0.2 mole. So for that, how much volume would be required? So volume is equals to 0.2 by 1. So uh, 0.2 liter of solution will contain 0.2 moles of NaOH. Okay. Now what we will do? We have to make it into how much? 1. See, what we have to do actually is to make a 0.2 molar solution. Right. Now we know that 0.2 liter of 1 molar NaOH contain 0.2 moles of NaOH. Okay, got it? Now, if we dilute it such that if we add 0.8 to this solution, then that would give us, means we are adding only solvent. So we are diluting it. So if we add 0.8 liter of solvent, that would give us again 1 liter, but the number of moles is fixed. Therefore, it will be 0.8. Got it? Clear? So this is a very good illustration to see the application of this molarity. Next, in fact, for such calculation, we have a general formula also. So we have two things. M1 is given, V1 is given, M2 is given, V2 is given. Okay. So we take M1 V1 into M2 V2. M1 V1 is equals to M2 V2. If we just say equate both of this, because we need same molarity, therefore 0.2 into 1000 mole and 0.1 into V2, that would give us 200 liters. Note that the number of moles of solute was 0.2 in 200 milliliter, and it has remained same, that is 0.2, even after dilution of up to 1000 ml, as we have changed the amount of solvent, and have not done anything with respect to NaOH. So this is very simple to understand, that we are taking the same solution which contains 0.2 moles of NaOH, but we are adding only solvent in that. So we are not changing the number of moles of NaOH. Therefore, the molarity will only change such that it will be equals to 0.2 molar solution. Next question, it is a very good question. It says that the molarity of NaOH in the solution is, in the solution prepared by dissolving 4 gram in enough water to form 250 ml of the solution. We have to calculate the molarity. So we are dissolving 4 gram in 250 ml. So how you will do it? First you have to calculate that how much number of moles is present in 4 gram. So for that you have to calculate the molar mass of NaOH. That would be 23 plus 16 plus 1. 6 plus 4, 10. 2 plus 2, 4, 40. Clear? So number of moles would be number of moles is equals to given mass by molar mass. That is 1 by 10 or 0.1 moles. Now molarity is equals to number of moles by solution, that is 250. Now it is given in milliliter. If we convert it into liter, that would give us 10 to the power 3 multiplied by 10 to the power 3. Okay, that would give us 100 by 250. Okay, 0.4 would be a molarity. So it is it has means the solution in the same way. Mass of NaOH by molar mass, that would give us 4 by 40 by 0.250. That would bring us to 0.4. So this is the molarity. Next is, what is molality? What is molality? So it is again the number of moles solute that is dissolved in 1 kg of solvent. So this is very important point to mention here. So students do the mistake that they take the mass of solution rather than the solvent. So the difference between the molarity and molality. So it is number of moles by volume of whose solution, whereas it is number of moles in what? In mass of solvent. First of all, we have taken volume, here we have taken mass, here we have taken solution, and in case of molarity, we have taken solvent. So this is very important. This is the formula. Now the third thing, it is represented as xm for molar, and for molality, it is represented x small m. So the molarity is equals to number of moles of solid by mass of solvent in kg. So let us do a question. So density of 3m solution is 1.25 gram milliliter, gram per ml. Okay, gram per ml. Calculate the molality. Density is given. For the solution, density is given. And the molarity is given. Molarity is given means in 3 moles is dissolved in 1 liter of solution. 1 liter of solution. Now 3 moles are dissolved in 1 liter of solution. Now in 1 liter, what is the mass of 1 liter? For that, we know that density is equals to mass by volume. We know that. Now density is given, volume is given, mass would be equals to density, that is 1.25 into 1. That would be 1.25 gram. Okay. Now it is given in gram per milliliter, not liter. It is given in gram per milliliter, not liter. So for that, let us convert this milliliter into liter first. So 1.25, so milliliter would be into, so density will be 1.25. So if you have to convert this milliliter into liter, we multiply by 10 to the power 3. Why am I multiplying and not dividing? Because milliliter is on the downside. So if we divide that downside by 10 to the power 3, that would come up and give density this much. So let me multiply it here only. Okay. That would give us 1250 grams. So this much mass is present. So 1 liter of this solution will contain 1250 grams. Is this clear? Now in 1250 grams is the solution. Okay. This is the solution. Now you have to calculate the molality. What you have to calculate? The molality. So how you will calculate it? How you will calculate it? For that, you have to calculate the amount of water or the volume of water that is present. Again, in 1 liter of solution. Okay, so in 1 liter of solution, how many mass of water is present? So we know that 1 mole contain 22.4 liter of water. Did we know it? Yeah, from our law. Okay. So in 1 liter, how many moles will be present? 1 by 22.4 moles will be present. Now in 1 mole, if 18 gram is present, so in 1 by 22.4, so 20.7 I think, yeah. So in 22.7 mole, how many gram? That is multiplied by 18. That would give you the mass of water that is present in 1 liter of solution. Once you get the mass, it is very easy to solve. Okay. So let us see the solution. So since density is this much, we have calculated the density of the solution. Now mass of water solution, as I have told you, if you subtract it, we will get the solvent. Okay. So that would give us 10, this is converted into kg. Say this is very important. Okay, this is also very important, that you have to get your mass into kg, not in grams, for calculation of molarity. This is very important to mention, as we have to take liters for volume in case of molarity, we have to take kg in terms of molarity. So this is very important to mention, right? Now if I ask you that which is more significant, so for gaseous atoms, for gaseous solution, we have this mole fraction. But what about this liquid state solution? For that, molality is not preferred. Instead of that, molarity is preferred. Okay. So what is the reason behind it? The reason behind is that the molality of a solution does not change with temperature, but mass remains unaffected with temperature. So this is the reason behind it. So molarity is kind of changed with respect to temperature. So it is defined for a given temperature. So therefore, we consider molarity rather than molality. One more important point: the solution of higher concentration is also known as Stock solution. So often in a chemistry laboratory, a solution of a desired concentration is prepared by diluting a solution of higher concentration. So in labs, what do? We prepare the solution beforehand, okay, and that solution is kind of having greater concentration. Now if we require a smaller concentration, first we have to calculate accordingly so that the concentration can be changed to that required amount, and then we will do the reaction. So this is very important. So a question can be asked from here that you're given a stock solution and you have to convert it into a given dilution that is given, then how many volumes would be required? Okay, so this is a very good question to be asked. So remember this term, that in left we have a very higher concentration that is present, that is called a stock solution, and we convert this stock solution into a required dilute solution. So this was for today's class. We have seen the very four important means of say representing the concentration. Instead of mass percent, we can also have volume percent. So that is also very easy to understand. So the volume, if you have to calculate the volume percentage for a given species, then the volume of that species divided by total volume into 100. That would give you the volume percentage, volume by volume percentage. It can be also volume by weight percentage. So the volume of the species for which you are looking for divided by the weight of the solution, okay, multiplied by 100. Clear? So with this, I end my lecture. Thank you.